we need DC simulation only. As we can see, the VTC is exactly as we expect it to be. But there is one problem. The VTC is not exactly in the middle, which make the inverter not symmetric. How can we fix this problem?
Hello everyone, this is your first video from Think Electronics. Today we will talk about designing a CMOS inverter. Just for a moment, let's assume that you don't know what the function of an inverter is.
In the fact, before start designing any electronic circuit, you must know exactly how it works. To understand how the inverter really works, first we will assume that the MOSFETs are switches. That is, basically the NMOS will be on when applying a high voltage on its gate, and the PMOS will be on when applying a low voltage on its gate. Here it is, the schematic of the CMOS inverter. So what will happen when we apply a high voltage input to the inverter is that the NMOS will be on and the PMOS will be off. So the output will be connected to the ground and gives us a 0. On the other hand, when we apply a low voltage input to the inverter, the NMOS will be off and the PMOS will be on, and the output will be connected to the source and gives us a 1. So what will exactly happen when we apply a square wave to the inverter? The output signal will produce exactly the same input signal but reverse it. It can be considered as multiplying the input signal by -1 or as offsetting the input signal by 180 degrees. Of course, this depends on many variables like the size of both NMOS and PMOS, the total power, the voltage headroom, and the value of output capacitance. For example, if the output capacitance is very high, the output voltage won't have enough time to charge and discharge its capacitance, and the output voltage will continue decrementing. If the output capacitance is very low, on the other hand, the output capacitance will charge and discharge very fast, leading to problems with the timing of inverter output.
Let's start our simulation of the inverter using Cadence Virtuoso Analog Environment and TSMC PDK. Open terminal and write new_virtuoso, then open tools and choose library manager. First, we want to make a new library, file, new library. Library here is like the parent folder that contains all the related files. We will name it Think Electronics and attach it to an existing technology library, then choose TSMC in 65 and click OK. Then we add a cell by selecting the library, then file, new, cell. Cell here is the file that can be simulated by Cadence. It can have many types like schematic, Verilog, VHDL, layout, or AMS. Cell also can have multiple types like schematic and layout at the same time, and this is used for LVS checking process. We want here to make a schematic of a CMOS inverter, so we choose schematic and click OK. A new schematic window will open where we can add our components. To add a new component, we hit I, browse. Then we select the library that contains that component. We won't add NMOS, so we select TSMC N65 and choose symbol of NCH. We can put it anywhere inside of the schematic window. After that, we add the PMOS the same way. While we are holding the component, we can hit F3 to edit its properties. Like here, we can edit the length and width of the PMOS. We will place it here above of the NMOS. You can cancel any command by hitting escape. Now we want to add a source and the ground.
They are located in Analog Lab library. It contains all basic components like sources, resistors, capacitors, and inductors. Let's add multiple VDDs. To undo a command, hit U, and to redo a command, hit Shift and U. We connect the VDD with the source of PMOS. Now we add the ground, which is found as GND cell inside Analog Lab, to the source of NMOS. Then we hit Escape. To wire both gates, we hit W and connect them. Then we connect both drains together. We also connect the bulk of PMOS with VDD and bulk of NMOS with ground. We need to add input and output pins to create an inverter symbol. Hit P, then write in as the pin name. Connect it with the wire connecting both gates. Hit P again and write out as the pin name. Change the direction of the pin to out. Connect it with the wire connecting both drains. We can also stretch a wire by hitting M, then select the object and move it, like what I am doing right here. We fit the schematic to the window by hitting F. We also can move the schematic window all around using arrow keys, or we can zoom in and out using square brackets. To save our schematic, we hit Shift and X. To move an object, we hit Shift and M, then select the object and move it. Now when we hit Shift and X again, a message is shown telling me that there is a warning. To read a warning, we close the message and hit G or Shift G. Let us return the pin back and hit Shift and X again. Now our schematic is finished and we will create a symbol representing it. We click on Create menu, Cell View from Cell View. A window appears telling me the details of the new cell view like the library and cell names. We hit OK, then another window appears telling me the details about the input and output pins of the new symbol. We also hit OK, then a new schematic window will appear. We can see now red and green boxes. We should take care of the red boxes as it is the boundaries of the symbol of the inverter, while the green box is the real shape of the inverter. We want to change the shape of the green box, so we delete the old one by selecting it and hitting delete. Then we add a line by selecting Create menu, Shape, Line, and we draw a triangle. We add a circle in front of the triangle by selecting Create menu, Shape, Circle, and we draw a small circle. After that, we adjust the location of in and out pins and resize the red boxes. In the end, we save our symbol by hitting Shift and X. Close both opened windows. As you can see, the symbol is ready and it's time to see some actual signals. Create a new schematic cell view, naming it test_inverter, then hit OK. Insert the symbol of our CMOS inverter from Think Electronics library. To buy the circuit, we need to add DC voltage sources. We need to add one here and another one here. We need also to add VDD voltage source and a ground. Then we add a capacitor at the output. Then we copy a ground by hitting C, then select a ground and paste it under the capacitor. After that, we wire the pins. We can name the wires by hitting L, then writing the names. Then we put them on the wires where we want to name them.
We can also add new text by hitting Shift and L and adjust its height and style. But we probably won't need it. Then we add a pin and connect it to the output. We can adjust the values of any component by selecting it, then hitting Q. Select the DC voltage source, then hit Q. Put one in the DC voltage area. Select the other DC voltage source and put V bias in its DC voltage area. Change the capacitance to become 10 femtofarad, then hit Shift and X. Now it's time to run the simulation. Click on Launch menu and select Analog Design Environment L. A new window will open which have different areas. First, we copy the variables from Schematic by selecting Variables menu, then copy from Cell View. Put 500 mV as the value of V bias. Then we select the Out menu. To be plotted, select on Schematic. Click on the names of the input and output wires to add them. We will start simulation by doing transient. So we select Analysis menu, choose, and we put stop time 500 micro. But first, we need to change the DC source. Choose the DC source and hit Q. Change cell name to be vPulse and hit apply. Change voltage to be 1 volt. Put a reasonable period of 10 micro and put delay time of 0. We need a symmetric rise and fall time, so we changed them to be 1 pico. Put pulse width of 5 micro and hit OK. Save the changes, then return back to EDEL and run the simulation. We can separate the two signals to see them clearly. We can also adjust the values of any curve by double-clicking on it and change it. Let's zoom in a little bit. As you can see, the input and output signals are exactly as we expected them to be, which tells us that the inverter is working correctly. Before we go to the next step, we need to understand the output pretty well. The idea of the inverter is to reverse the input signal. That is, when the input is low, up to a certain point, the output is high. And when the input after that point is high, the output is low. And if we try to draw the voltage transfer characteristics, it will be something like that. We can divide the VTC into 5 regions. First region is when the input signal is very low, so the PMOS is on and in triode region, but the NMOS is off. Second region is when the input signal starts to increase a little bit. The NMOS enters saturation, but the PMOS is also connecting and is still in triode. Third region is when both NMOS and PMOS are connecting and in saturation. After that, the inverter enters the fourth region when both transistors are on, but NMOS goes to triode. And final region is when the input signal is very high and close to VDD. So PMOS is off and the NMOS stays in triode. After understanding the VTC of the inverter, it's time to run the DC simulation and see the output. To a DC simulation,
We open Analysis menu, choose. Click on DC and choose Design Variable. Select Design Variable V-Bias. In the sweep range, put 0 as a start and 1 as a stop. Then hit OK. Before we run the simulation, we need to change the pulse voltage source to be DC voltage source. Then hit Apply. Then OK. We need DC simulation only. As we can see, the VTC is exactly as we expect it to be. But there is one problem. The VTC is not exactly in the middle, which makes the inverter not symmetric. How can we fix this problem? To understand this problem, we need to go back to the ideal VTC. What we need is to increase the length of region 1. So the inverter becomes more symmetric. In this region, NMOS is off and PMOS is in triode. We can increase this region by simply increasing the width of PMOS channel. So NMOS will need higher gate voltage to become on and go to saturation. To do this, we go back to the schematic. We select the inverter, then hit Shift and E and click OK. This will make us descend to our inverter schematic. Select the PMOS and change its width to be WP and hit Apply. Then select the NMOS and also change its width to be WN. Then hit Shift and X to save changes. Hit Ctrl and E to ascend back to our simulation. Return to ADEL and select variables. Copy from cell view. Put a value of 200 nano as the width of NMOS. Now we want to increase the width of PMOS. Write 300, then change the plotting mode to be append to see the difference. We need only to see the changes in the output. As we can see, the VTC now is shifted to the right, but we need to shift it more. Change WP to be 500 nano and run the simulation. It's better, but we need to shift it a little bit more. Zoom in to see the VTC more clearly. Change WP to be 550 nano and run the simulation again. Again, change WP to be 575 nano and run the simulation. That's much better value for the width of the PMOS. In general, most devices have very low static power consumption, which happens when the transistors are in off state. It occurs when all inputs are held at some valid logic level and the circuit is not in charging states. But when switching at high frequency, dynamic power consumption can contribute significantly to overall power consumption, and it happens when transistors are in on state. Charging and discharging a capacitive output load further increases this dynamic power consumption. We start explaining the static power consumption, which derives from the transistor channel length as well as doping level and gate thickness. In reality, all MOSFET transistors
the current between the source and the drain. If there is a voltage potential across that source drain channel, even if the gate voltage is in off state. The gate oxide, which serves as insulator between the gate and channel, should be made as thin as possible to increase the channel conductivity and performance when the transistor is on, and to reduce subthreshold leakage when the transistor is off. However, with decreasing thickness of the insulator, the quantum mechanical phenomenon of electron tunneling occurs between the gate and channel, leading to increased power consumption. Increasing doping level allows higher on current for faster operations, but causes also higher leakage current. This produces a current of minority carriers, and hence its magnitude is very small. Dynamic power consumption is due to the current that flows when the transistors are switching from one state to another. This is a result from switching current plus the current that flows from source to ground when the PMOS and NMOS transistors are on briefly at the same time during the logic transition. For fast input transition rates, the dynamic current is governed by the internal capacitance and the charge and discharge current of the load capacitance. Dynamic current is dominant in CMOS circuits because most of the power is consumed in moving charges in the parasitic capacitance in the CMOS gates. Static power consumption is the product of the device leakage current and the supply voltage. To minimize leakage current, we can either lower operating voltage or stack fewer leaking transistors on the same area. On the other hand, we can reduce dynamic current by either lowering operating voltage, decreasing load capacitance, or reducing operating frequency. Let's go back to our simulation to get values for both static and total power. First, we need to measure static power of the inverter. Click on Output menu, Save All, and check All in both. Select Power Signal to output PWR and select Device Currents, then hit OK. Open DC Analysis and uncheck Design Variable and hit OK. Uncheck both outputs, out and in, then change V bias to be 0. Then run the simulation. When the simulation is complete, open Tools menu, Result Browser, open Train, and right click on PWR and choose Plot Signal. This is the static power of our inverter when the inputs is 0, which tells us that it comes mostly from the NMOS. Open Marker menu, Place, Trace Marker, and click on the output. We have a static power of 2.123 nanowatt at gate voltage of 0. As we know that static power mostly comes from NMOS, so we can change the width of NMOS to see the difference in static power. Let's try a value of 475 nano and do the same steps again. Roughly speaking, the static power is almost doubled when we double the width of NMOS at 0 gate voltage. We can run the simulation for different values of Wn. To do this, open Tools menu, Parametric Analysis.
Then open sweep menu, parametric set. We put Wn as variable name, and we put values of Wn at which we want to find the static power. Then select analysis menu, start. Go to tools menu, result browser, right click on PWR and choose plot signal. There are 4 values of PWR or power at each one of Wn. It is clear from the simulation that the value of static power depends mostly on the width of NMOS at 0 gate voltage, and it increases proportionally with the increase of Wn. Now it's time to measure the total power of our inverter. To do that, we go back to the schematic and change the DC voltage source to be pulse voltage source. Then we add the same old values and hit OK. Hit Shift and X to save the schematic and go back to ADEL to run the simulation. When the simulation is done, open Tools menu, Result Browser. Right click on PWR and choose Calculator. Then click on Average function, then hit Evaluate. A result of 6.314 nanowatt appears. To see another result, go to the schematic and change the values of the capacitor to be cap. Go to ADEL and copy variable from cell view. Put a value of 10 pico to the capacitor and run the simulation. Then we apply the same steps again. Now, as you can see, the power increased significantly when we increase the load capacitance from 1 femtofarad to 1 picofarad. That tells us that the total power depends mostly on the value of the load capacitance. Now we found both values of the total and static power. To find the value of dynamic power, we can subtract the static power from the total power, and this will give us the dynamic power. Here are some results of both the static and total power of our CMOS inverter. From the results, we can see that the static power depends on Wn when the input is low and depends on Wp when the input is high, while total power depends on the load capacitance, and it gives us results of microwatt when increasing it to be more than 10 picofarad. If we are interested in lowering the power of our CMOS inverter, we can simply adjust these parameters so we can get the total power as we want. But we have to change them carefully, as we saw before that the width of both NMOS and PMOS affects directly the symmetry of the VTC, which have great impact on other property that we will talk about later. Okay, in this video we learned how to design a CMOS inverter. We use this schematic to make a symbol of it, which we use later to do both transient and DC analysis. We learned also how to adjust both the VTC and power of the device. If you found this video useful, like it and subscribe to the channel. And if you have any questions or comments, please leave them in the comments area. And thank you all for watching.